So far in our study of simple harmonic motion, we've been looking at equations that involve time. We're now going to look at an equation for velocity where we don't actually need to know the time throughout the period that we're looking at. We only need to know the displacement as well as the angular frequency and the amplitude. Now, the derivation that I'm about to show you here, it's not something that you actually need to be able to reproduce, but I find it helpful just to show the steps so that you know this equation is based in these initial equations that we've been dealing with already. So ultimately, all you need to be able to follow here is that there is an equation at the end that is in the data booklet, and just to be aware of where you might use that equation. So if we start out with the equations that we've seen already, so I'm going to use the sine and cos versions of displacement and velocity respectively, but you could do the same thing using cos and negative sine for displacement and velocity. Either way, the derivation would arrive at the same endpoint. The other thing that we need to use here though as well is a trigonometric identity. So hopefully you've covered this in maths somewhere. If not, let me know and we can have a quick discussion about it in class, where this identity comes from. The identity that we're dealing with is sine squared theta plus cos squared theta being equal to 1. So that's the identity that we're going to deal with, and we're going to just manipulate it a little bit. So we'll take it to cos squared theta being equal to 1 minus sine squared theta, and take that one step further, so we've got an expression for cos theta. That's then going to be plus or minus the square root of 1 minus sine squared theta. So there's a bit of algebra to get another expression for cos theta. So if we now take this identity here for cos theta and we use it in this equation up here for velocity, what we're going to see then is that the velocity v is going to be equal to, I'll just write that again so we've got it handy on screen. So that's going to be cos omega t. So in this line above where we've got theta, we're actually going to substitute in omega t instead. So v is then going to be equal to x naught omega multiplied by the square root of 1 minus sine squared omega t. Now notice that I haven't put this plus or minus in yet. That's because I'm going to put it right at the front here. So we've got those two possible answers, the positive and the negative answer. So there's another step that we can take. But if we go back to the initial equation for displacement, we also can identify that sine omega t would be equal to x over x naught. So that's just dividing both sides by x naught. So starting off with x is equal to x naught sine omega t, we can end up with sine omega t is equal to x over x naught. And if we then square both sides, we'd end up with x squared over x naught squared. So we can make that substitution. So this part here, given that it's equal to sine squared omega t, we can substitute that into that part of the square root term. So we then would have that v is equal to plus or minus x naught omega multiplied by the square root of 1 minus x squared on x naught squared. So notice now we don't have any terms in t. It's all to do with the displacement, the amplitude and the angular frequency. We can simplify this a little bit further though, and the way that we're going to do it is just basically algebraic steps here. So let's go through those quickly. The first thing that we're going to do is we'll leave the omega term here out the front, but we're going to take this x naught term here and we're going to sort of propagate it into the square root itself. So if you think about x naught, we could instead write that as the square root of x naught squared, and that would then all be multiplied by the other square root term that we have there as well. So the reason why we're doing that is to collect all of these x naught terms. So the next step then, if we're multiplying two square roots together, we can simply multiply through across both terms, but keep in mind here we've got this subtraction term in the middle. So that x naught squared needs to be multiplied across both terms. So basically going to have x naught squared minus x naught squared multiplied by x squared over x naught squared. So that means that these two x naught squareds are going to cancel, and so we'll be left with v is equal to plus or minus omega multiplied by the square root of x naught squared minus x squared. And that's the equation that you will find in the data booklet. So you can see there that if we know the amplitude and we know the displacement of the particle, as well as the angular frequency, we can then figure out the velocity without first having to calculate the time. So it's just sort of a quicker way to go from the displacement to the velocity, rather than having to worry about finding the time first and then substituting that into the velocity. V is equal to x naught omega cos omega t, and so it just speeds up that process a little bit. We'll have a look at a few more problems in class using all of these equations for simple harmonic motion, and really just make sure we've got these under control before we move on to the next little bit of content about pendulums and masses on springs.